talk will be a lot more on the synthetic data side of things, but the topic of the workshop is actually really close to my heart because in many ways, a lot of my machine learning work has been on robustness. And actually the reason why I've been studying language models and sort of scaling behaviors of language models is because of their connection actually to robustness. So to give a little bit of context, I've been just kind of shocked at how good language models are. I'm a sort of natural language processing and statistical machine learning researcher. And when GPT-3 came out, I think many of us, both in machine learning and NLP, were kind of shocked at just how versatile it was. If you sort of remember, the days of BERT and fine-tuning models for task-specific goals, perhaps you remember sort of models that you would, fine-tune on really specific tasks, and then they would sort of be brittle and break once you sort of deployed them outside their context. A lot of the large pre-trained models that we have today don't really seem to have these same behaviors. And that was just kind of a really eye-opening moment for me, because I'd spent many years working on sort of algorithmic approaches to robustness. Like, how can we find better loss functions? Can we train them adversarially? Can we get them to generalize out of their domain? And I think, the same sort of empirical goals were, in fact, very easily, or at least, intellectually easily, attained through, large-scale pre-training. And so that really led me to try to understand what is going on with this, pre-training thing, with this foundation model thing that is really, changing the way that we work on machine learning and AI. And so today's talk will be sort of centered on that sort of empirical question of, we've seen that these models have these really remarkable capabilities, their ability to generalize out of domain. And so I would like to try to understand what is going on and to use synthetic data to try to both understand and to improve these systems. So with that background, I want to talk a little bit about context. We've seen sort of these models, these large language models, get remarkably good. And backing that is sort of this phenomenon that you might call scaling, right? So increasing both the size of the models and the amount of data that is used to train them. You might remember GPT-2. That was a long time ago now. This system was good for generating text, but really not much else, right? You wouldn't use it to, do any sort of real-world downstream task. But then with, pre-training scaling, so using much more data and larger models to train these sort of essentially autocomplete systems, we saw really predictable improvements up until, ChatGPT 3.5. And then much more recently, you might have heard sort of popular talk about sort of reasoning models and so on. That's a different kind of scaling, thinking for longer or inference scaling. And so I'm really interested in this question of how can, predictable investments in resources like data lead to predictable gains. Often people talk about power laws. So essentially polynomial improvements in model performance as a function of resource inputs. So you might think of the resource inputs as more computational power, more data. I'll talk more precisely about what these things are. But these things, I think, have been really interesting because of just how consistent the gains are in the last couple of years. We're beginning to see diminishing returns on some of these sources of sort of scaling. But I think pre-training, for example, the task of using large-scale internet data and training models to predict, let's say, the next word, is reasonably efficient. You see exponents of, let's say, 0.2 to investments in compute. And they've held up over many orders of magnitude. So one sort of fun trivia is when you look at GPT-1 and you look at DeepSeek v3, that's about 10,000 times more compute investment. And actually, the gains to that compute have been relatively predictable over that period. At the same time, I think sort of 2025 is a really interesting time to be thinking about these questions of language models and synthetic data and where does this field go? Because I think we see lots of evidence that, continued scaling, like making models bigger or dumping more compute at the problem, maybe isn't going to solve the problem. And I think one commentary I'll make here is we're beginning to really see the limitations that come from the differences between sort of, I would say, like human and computational learning. We see that new pre-trained models like GPT 4.5, which was released a few months ago, really kind of in some ways hitting a wall, right? GPT 4.5 is much larger. It's about 35 times more expensive than the previous models. But it's actually not even sort of the best model out there, right? Even OpenAI says, oh, it's actually not a frontier model. And Ilya Sutskever, in his Test of Time talk at NeurIPS, he has quite the way with words. was saying, well, pre-training as we know it will end because data is not growing, right? It's the fossil fuel of AI. And so I think this calls into question, or at least, makes us really examine what is going on with this kind of learning and how we might sort of go beyond it. And I think one of the things that I've been thinking about a lot is just how different language models and humans are, right? In both the ways in which they generalize, but also the ways in which they learn, which I think is quite important. If you think about what large language models are trained on, well, they're trained on large swaths of the internet. I think the most recent Qwen 2 model that was released maybe a week ago was trained on 36 trillion tokens. That's just kind of an astounding amount of data to be trained on. It's probably most of the high quality internet that you can get your hands on. And there are arguments that people have made that I think are starting to be borne out in empirical observation, that essentially most of the useful stock of data on the internet is being used up for pre-training. So that's a plot on the right from Epoch AI, where they made a projection about a year ago on when basically useful data from the internet will be used up in pre-training runs. And I think they made a forecast about 2027. But I think maybe more realistically, we're starting to see some of those diminishing returns already. And I think the interesting questions that this raises is, can we more efficiently learn from the data that we do have? And maybe importantly, for a lot of the applications that these systems are being deployed at, can we adapt them to a lot of the sort of more narrow proprietary domains that they're being used for, right? I think the days of saying, we're just going to take as much data as we can from the internet, we're going to build this one gigantic generalist model by sort of building bigger and bigger data centers, that doesn't really seem like it's going to pan out, right? And so we're going to have to think a little bit more carefully about kind of the nature of learning and maybe adapting these models to specific domains. So if you go and talk to folks from OpenAI or Anthropic about this current situation, they'll say, oh, that's fine. Don't worry about pre-training hitting a wall or us running out of data or our algorithms being horrifically or data inefficient. Okay, that's all fine because there are these things called reasoning models, which just kind of think for longer at deployment time. And if you do that, then, well, it's going to be okay. Our models will be smarter. We'll have a new axis of scale. I think the thing that's been frustrating for me over these past few months, I think ever since OpenAI released o1, was there's really no great science, or at least until very recently, about what this thing actually is. I like to sort of bring this point up in every talk I give, but this left plot is what sort of OpenAI released when they sort of announced o1, and maybe you'll notice that their x-axis on their plots don't actually have labels anymore. In the interest of secrecy, they can't even tell us how many flops are used in each one of those dots when they do this training. And so I wanted to really, a few months ago, I wanted to really understand what this object was, right? Like if reasoning, supposedly, is the future of my field, well, it behooves me to understand what that exactly is. And so I want to talk about sort of two sort of major things, two projects that I've been working on, and sort of in the context of synthetic data. Synthetic data is really interesting to us because it allows us to sort of intervene on these models in sort of very precise, targeted, and data-centric ways. And I'm going to use that in the first part of my talk to try to understand these reasoning models by sort of coming up with different ways of making them in very simple ways. And in the second part of my talk, I want to try to use synthetic data to make learning much, much more data efficient. So this is sort of improving models using synthetic data. And since this is a workshop with really diverse interests and really diverse topics, I'm going to try to make connections whenever possible to kind of the biological aspects of robustness as I go. So I think this discussion about reasoning models has particularly been interesting to me because it's taken really, I don't know, I would say like a really pseudo-scientific tone sometimes. I've taken sort of Jensen Huang's keynote because I think this sort of captures a lot of what I'm frustrated by, including the fact that this plot doesn't really make sense. There's 3 phases of scaling, and reasoning scaling's on the right, but somehow the reasoning scaling's the worst of the 3, and you would do that one because I'm not sure why. I think many have argued that this new notion of thinking harder is kind of the way the future of this field will go, right? And what does that really mean? And I think we've seen lots of suggestions that this is a really qualitatively different object, that this is really going to be powerful. And I think sort of as humans, we think of reasoning as like a really core capability, right? No matter what new domain that we go to. For example, if I were to try to learn law tomorrow, right? I would use my reasoning capabilities to be able to learn that more quickly. I would use those capabilities to try to, operate well in that domain. And so this is sort of a really important question to be able to say, what is this new sort of general capability that we're acquiring here, right? I think one thing that was very interesting to us when sort of, when the first reasoning models were released was that it really did at the time look like a totally different thing. So on the left side of this slide is, OpenAI's o1 when it was released. And as I was saying at the beginning of this talk, one of the interesting things about this is this notion of scaling, that on the x-axis is, the amount of compute I spend, the time I spend thinking. The y-axis is the performance, and it's predictable, right? And you might, if you look at this plot, you might be sort of led to believe that, oh, I can just keep thinking for longer, and my AMI accuracy will continue to go up and up and up, right? On the right side, several folks, Epoch AI included, did some early sort of investigations into this model, and they sort of found that, wow, these new reasoning models can attain performance that is very far out of reach from models that are using different kinds of sort of inference scaling. So in this case, you can think for longer by just sampling more outputs from the model and then taking a majority vote. That's the teal line that's on the bottom. Or you can ask the model to continue revising its answers. That's kind of the blue line that you see there as well. And those two lines sort of don't have the same kinds of scaling qualitatively as this O1 model. And so we really wanted to understand what was going on. And I think one of the things that's interesting to us is there's a potential that these kinds of sort of reasoning models are a totally different ballgame. In the same way that sort of AlphaGo and search algorithms and so on are very, very different from the machine learning systems that we normally use and operate today. And I think sort of public discussion sort of mirrors a lot of this very often. I've taken a little clip from Yoshua Bengio's sort of public-facing opinion piece in the Financial Times, where he says, oh, these models, when they spend more time thinking for longer, they get much, much better. And I think one thing that's very, very interesting, and this is a subtle point, but I think an important point, is whether these models are really extrapolating, right? So this is the question of, in some ways, robustness and generalization. If you look at models like AlphaGo, you'll see that they're trained with a certain amount of training compute. And when they're deployed, they spend a lot more computational power sort of doing search, right? So their inference compute is much, much larger than their training time compute. And in many ways, they generalize very well at inference time, using out search algorithms. On the other hand, language models don't have this property, or at least current generation language models don't have this property, right? They're trained with a certain amount of compute, and at inference time, they're deployed and they use that exact same amount of compute. They don't really think for longer unless they're using more sort of tokens by explicitly sort of verbalizing their thinking, right? And this is, of course, an important distinction. I'll sort of touch on this as I go on. You see this even in AlphaGo, right? In AlphaGo, they show that, if you do search, you get this nice blue tall bar. This is the AlphaGo 0 model that sort of least it all. And then you have the raw network, which doesn't do any search. That's thinking for as long as it was trained. And it's much, much worse than kind of the best models. And so my students and I were very interested in this gap, right? Are these models really truly generalizing, right? A reasoning model should be able to think for much, much longer than the situations it was trained for and get much higher performance, right? If, on the other hand, what we're doing is we're just training the model with more and more compute, right? It's, of course, reasoning training, so they're going to get better at math, but they're maybe not generalizing. And that does really qualitatively change the nature of what we think of with these reasoning models. So I'm going to take a moment to sort of, discuss sort of just the science of science kind of stuff for a moment here. One thing, as I said, that's very frustrating is that a lot of these, processes are closed source, and they're also very, very computationally expensive, right? When OpenAI o1 initially came out, we knew very, very little about what they had done. They were so cagey that they didn't even really say whether they did reinforcement learning or they did search or anything else. And so in this subpart of the talk, my goal will be kind of like, in some ways like a biologist. What I'm going to look at is the phenomenon, the empirical phenomenon that we see externally. And I'm going to try to replicate this. So I'm going to care about the phenomena and not necessarily some underlying process that generated this, right? So I don't want to match OpenAI. I want to try to understand this particular scaling phenomenon. So to be concrete, I'm going to come up with some method that will give us inference scaling from 20 to 80% accuracy on AMI. So this is the high school math exam. And I want to do dramatically better than just majority voting on my models. And so, several of us sort of set out with this goal to try to understand reasoning models and whether they're generalizing and extrapolating and so on. And so we tried a lot of different things. We used a bunch of reinforcement learning algorithms. We used all the search algorithms that we found that people had worked on. But none of those really worked very well. And I think one of the things that I learned again and again in machine learning or recent machine learning is that very, very simple things often work really well. And data-centric interventions also work really, really well. And so what had worked in the end was to basically come up with a really simple synthetic data style data set. So what we did was we went out and we collected a small number of math and sort of reasoning data sets. So here we had gone out to Newman and Math and several other sort of high quality sort of math question sources. And you can see sort of the diversity of the questions that we collected here. And one of my students, Zitong is a stats student, and so he and Emmanuel were interested in the question of can these AI systems do the statistics qual, so they threw that in there too. And so we ended up with about 1,000 math and sort of science, or not science, math and reasoning questions that we basically used as a high quality curated data set. And then what we did was we did the simplest possible thing on this data set, which was to go and take an existing sort of reasoning model, in our case, Gemini 2.0 flash thinking, and take sort of the verbalized reasoning traces that these models output, and then just train our model, which in this case was a Qwen 2.5 32B model, and then just fine-tune that model on these reasoning traces, right? So this is a very, very lightweight intervention. We're taking a open source or open weight model that doesn't really do very much of this like reasoning, steps. We take the reasoning steps from an existing thinking model, Gemini 2.0, and then we just do a little bit of fine-tuning on 1,000 examples, right? So we're not fundamentally going to teach it new capabilities with that little data. And what we get is actually quite surprising, and at the time we thought was pretty remarkable, which was, with very, very few examples, we get math sort of benchmark accuracy that is remarkably good, right? We've gone from Qwen 32, which is 84% on math, to 93. On Amy, the difference is more dramatic, going from 26% to 56.7. And so just 1,000 math science questions and a few long chains of thought from Google's Gemini model just gives us this remarkable bump in performance. But I think this alone wasn't really my core interest here. I don't necessarily want to just like build models that can answer math questions. OpenAI is certainly much better than me at doing that. Really, my interest is in understanding extrapolation and generalization, right? And so, as I said before at the start of this part of the talk, my interest is in, understanding scaling, right? So is it possible for models to think for longer and then do better on their benchmarks? And so we had, or one of my students had, a very, very simple idea, which is to say, well, we want the model to think for longer. Like, could we force it to verbally think for longer? So, to give some context, right, when a language model is asked to sort of think through a problem, right, we use chain of thought, which means, it verbally sort of expresses its thinking process. And what we do is we try to hit a target length for COT. So we try to force it to think for a particular length of time. And if, for example, the actual chain of thought for a model is shorter than that target, what we do is we sort of suppress the end of thinking token, which is a special marker that switches the model from thinking to answering. And then we output the word wait. And that's just kind of a little verbal trick, because once the model says wait, then it just sort of starts, rethinking the previous thinking trace and continuing on as before. If our chain of thought length is above the target length, we immediately truncate the chain of thought. We emit the end of thinking token, which forces the model to just immediately switch to the answer. This nearly perfectly enforces the COT length, unlike doing prompting or sort of even training the model to try to get a particular COT length. And we attain sort of our goals. So this approach, called budget forcing, gives very smooth scaling, as we saw before. And I'll go through each of these two panels in turn. So the very first goal that I said we had was to try to replicate this plot from OpenAI's O1, where on the x-axis is kind of the thinking time, so the computational budget spent for these models to think. And on the y-axis here is the accuracy on a math benchmark. And on the right is OpenAI's O1 blog post. On the left is what we got from this like budget forcing and this S1 sort of distillation approach. What we see is both good and bad, we see qualitatively a plot that looks just like the OpenAI O1 plot. But I think if you look very closely, this plot is actually a little bit disappointing. So this dot here around 6,000, this is the model where we don't control its sort of thinking process at all. That's its sort of natural COT length. And then by using this approach of sort of forcing it to think for longer, we can sort of bump the performance up. We can go from 6,000 to a little bit higher on the right-hand side here by doubling 4 times and then 6 timesing its budget, right? So we do see a little bit of extrapolation beyond its training point. And so in some ways, that's good, right? I was interested in extrapolation. I did get some extrapolation. But what I had hoped at the very beginning of this sort of project, and I think what would have convinced me that this is a truly kind of new paradigm, is if we start at this very left bottom here, if we get a model that's really bad at math, right, that thinks very little, and then by forcing it to think for longer and longer, we can get up all the way to 60%, right? So extrapolate from the very left bottom all the way to the right top. That would have been very remarkable to me. But actually what we found was a lot of what was happening was, this left side of this scaling plot is actually just sort of truncating the thinking process. Of course, I can't say this is what OpenAI or others are doing, right? Like we don't really know what the others are doing. And of course, they're doing various kinds of RL. And so that's a qualitatively different phenomenon. But one thing is quite clear. Modern language models, even with pre-training and without any reasoning training, are good enough to get pretty high scores on these benchmarks. And so a lot of the scaling plots that we see is not the result of kind of robust extrapolation in the amount of thinking budget. It seems to be a lot more about sort of small amounts of extrapolation with large amounts of sort of, early exit or stopping thinking. And of course, just to complement the other plot, I said, what was my goals? My goal was to produce 2 plots, one that replicates the smooth scaling, the other one that kind of matches this Epoch AI report that compares, sequential scaling, the thinking for longer versus majority voting. And we kind of can replicate almost exactly that plot as well. And so that was really satisfying in many ways because we had set out with a very clear goal. Like, can we come up with a really simple method that, recapitulates qualitatively what's going on here? And we managed to do that. And so I want to end with 2 other interesting observations we made that I think others have also made since then. So the first one was, what other things could we do? So the approach we took was very synthetic data oriented. Could we come up with some, constructed chains of thought? Could we put that into the model? Can we use that to control the output of the thinking time of the model? One of the first things we tried though was to just use a normal model, have it think for a little bit, and then rejection sample, right? Just keep sampling until you get a sort of thinking trace of the appropriate length. One of the funny things that we found was actually if you do this, performance goes down as the model thinks for longer. And this is because the longer COTs are far, far out of distribution, right? And so even though we see a lot of sort of robust generalization with these modern language models, one of the things that we do still see is a lot of out of distribution effects, right? I think my results are very much consistent with the fact that these models really aren't kind of like magically generalizing. Here, if you just sample for longer COTs, they're qualitatively much worse. In the previous slides, I showed you if you try to force the models to think for longer, they'll do a little bit better, but then they'll sort of hit diminishing returns pretty quickly. If you apply things like majority voting or search, that can continue the scaling behavior, but the rate at which things scale is not particularly favorable. So I don't think that is looking particularly good. So okay, so what's the point of all of this? I think in many ways the most optimistic story for a lot of these reasoning models involves extrapolation, right? We train for a fixed amount of time, and then we deploy them, and we spend a lot more inference time compute. And due to extrapolation, they're able to solve way harder problems than they were trained for, right? I think that's the most optimistic case for these systems. As far as we know, there's not really evidence for that kind of extrapolation and scaling. And I think these models are remarkable. We know they worked. We know they're hitting really just new high water marks on math and reasoning tasks. But maybe they work really well not because they extrapolate in the sense that they think for much longer at deployment time, but maybe because the kind of post-training that they receive, the math training that we have developed using reinforcement learning algorithms are sort of really, really good. And so what that means is maybe a lot more compute spent still at training time rather than at deployment time. And I think that's a really interesting sort of conceptual thing to be thinking about and in keeping in mind. So okay, So that was about inference scaling. And now I want to talk a little bit about the original sort of paradigm. So I've been talking about the new paradigm, so to speak, of reasoning models. But now I want to talk about pre-training. And I think pre-training is really interesting because despite its astounding success in bringing us models like GPT-4 and DeepSeek V3 and so on, we also know that this is actually kind of a crazy learning algorithm, right? Because we're learning to predict the next word, and we're using that as a way to solve all sorts of downstream tasks. And the data inefficiency of this approach is really staggering, right? We're using trillions and trillions of tokens to get models that are less knowledgeable, than a graduate student in niche domains. So once we begin to run out of data, what are we going to do? We need to make language models much more data efficient. But that's really hard, right? We need new kinds of algorithms. We need new kinds of ideas to do that. And so some students and I came up with a kind of interesting setting in which we can study some of these questions in detail without having really large-scale compute. And so this is the setting of continued pre-training, in which you're given a pre-trained model F. And the goal is going to be, I want to teach this model facts within a niche domain. And so imagine you have a textbook, like a neuroscience textbook, and you want to teach the facts from this textbook into the model, right? This is a very data-constrained setting. I only have a few textbooks. And I need to come up with new learning algorithms that can enable this. Right? And if we can achieve that, we will have developed, significantly more data-efficient algorithms. We will have new domain adaptation algorithms that allow us to generalize to new domains. So I think this is a very exciting problem in general. I'm not the first to think about this problem setting. Continued pre-training is a very classic area of research. Domain adaptation is an even older, even more classic area of research. But I think continued pre-training has been an area that has been very challenging to work on because there have been really successful examples of people working on, medical or code or math models, but they've required billions and billions of tokens, right? I think the smallest successful case of this has required something like 15 billion tokens. And so as a sort of thought experiment, if we're really interested in having models learn from very little data, like a single book, right? We really need to push the limits of this kind of continued pre-training. And so I want to try to train models with 10,000 times less data on about 1.3 million tokens. This is a collection of about 100 books or so. And so why is this a difficult task? It's because pre-training is in many ways very, unhuman-like way of learning. It's incredibly data inefficient. What we're doing is learning to predict the next token, and the sort of representations learned by that in the model are supposed to be useful for downstream tasks. But it turns out that this process isn't as data efficient as we had hoped. I'll give you one example of this. There's a phenomenon known as the reversal curse, in which if you train a model and the model knows about, or it has been trained, in its pre-training data set, it knows the facts like A is B. It doesn't necessarily know, the reverse, the B is A, even if they're equivalences, right? So in this case, I have an example of, I've taken the abstract of my paper, synthetic continued pre-training is X and Y. In the autoregressive direction, the model probably learns this very well. If you ask, what does synthetic CPT do? That's an easy task for the model because it's been trained to, take in synthetic CPT on the prefix and output its definition on the suffix, right? But if you reverse it and say, here's a definition, what does this correspond to? That's a much harder task, right? And so the algorithms and the methods that we use to train these models really put limitations on the efficiency by which we can learn. And so the empirical results really do reflect this. So we take our 100 books or so, and we've chosen a data set such that those books come with their corresponding question answering questions. And let's say we just do continued pre-training. So we take those books and we just learn to predict the next word. Then actually we get the green line, which is worse than the dashed black line. So the dashed black line is our starting model. We train it to predict the next word on our books. We got this green line, which is actually just worse than what we started before. And that's because there's just not enough tokens in here for the model to learn anything useful. But we know pre-training works, right? And so we know that there has to be a way, in some ways, to bridge this gap. If we could take the data set that we do have, these books, right, and we could rewrite them in various ways, such that it sort of matches the diversity of pre-training data, the stuff that we see on the internet, then we should be able to actually teach these models these facts robustly. An analogy I like to use here is we know that models, know all really detailed facts about Harry Potter, right? But there's only really one Harry Potter book, so to speak, one original book. It's just sort of been, analyzed and rephrased and rewritten in many, many different ways on the internet, right? And so if we could replicate that process of taking a single sort of source of knowledge and then expanding it via augmentations, then it might be possible, even with existing learning algorithms, to get much, much more data efficient algorithms, right? So this is the idea of synthetic continued pre-training, and the idea of using synthetic data to try to really change the data efficiency of these models, right? So the goal here is just really to increase the diversity of what we have, rather than trying to say improve the compute efficiency of models or to fine-tune a really task-specific language model, right? My goal is still to have a generalist model. It's just also to have to inject a niche domain of knowledge into it. So one of the things that we could do is to do something pretty naive but actually pretty effective. You can just ask a language model, in this case GPT-4, to go and paraphrase these books, repeatedly, right? And so what that gives you is a very naive but useful augmentation. And this augmentation really does work, right? On the x-axis here is the amount of synthetic data that we're using to train the model. And the blue line now is repeatedly rephrasing random parts of the book. And you see that, as we increase the amount of rephrasing of the same content, the question answering accuracy of the model trained on this sort of improves and improves and improves, right? And so one way of thinking about this, I think, synthetic data gets a lot of sort of mystical discussion around it, but this is really just data augmentation, right? In 2025. We're coming up with good ways of adding variation and invariances to our model by rephrasing the original data that we have, and that gives us significant scaling improvements, which is quite nice. But then we sort of run into a problem, which is that LLMs are not terribly diverse. If you've interacted with ChatGPT or any of these systems, I think you've had the experience of these models sort of outputting a few things and then it repeats the same stuff after a certain point. And that's been our experience as well, and the experience of many others working in this area of using LLMs to generate data. So one of the experiences that I had was I had worked on with some colleagues and a co-advised student of mine on using LLMs to see if it could help us generate novel new ideas. One of the things we found was initially it can come up with a bunch of interesting ideas, and then about 500, after 500 of those, all the ideas that it generates past that point are duplicates of things that it has already generated, right? So there's just not that much stock of new novel ideas in a language model. And so an increasingly common thing that people have done over the past few years is to essentially inject external sources of randomness into this generation process. Like LLMs are not very good at being spontaneous and random, in many ways just like any single person is. And so we inject external randomness. And so in this case, we're going to take sort of inspiration from knowledge graphs. And what we will do is we will take each, let's say, document or each chunk of a book, and we will enumerate all of the entities that appear in that document. And you can imagine this as sort of listing out the entities in a knowledge graph. We're not going to explicitly construct this knowledge graph, but you can sort of mentally keep that picture in your mind. And then we're going to sample random entities in this list of entities that we have. So you can think of this as sampling pairs or trios or some subgraphs of this knowledge graph. And then we'll take a language model that's sort of large and been pre-trained, a domain agnostic one. And we'll ask it to synthesize the relationships between the entities that we've selected. So to give an example, imagine we have this document talking about Mona Lisa and Da Vinci and the Louvre and some people visiting these places. The document may never explicitly mention the relation between, let's say, Da Vinci and the Louvre, but if I pick these two random entities and ask the LM to discuss their relation, it can see that Da Vinci painted Mona Lisa and Mona Lisa is in the Louvre. That's all in the document. And it can now explicitly construct the fact the Louvre contains many works by Da Vinci, right? And so this is essentially taking implicit facts that are implied, by implicature in the document, and then making them explicit so that even an inefficient learning algorithm can learn them very easily, right? So we're sort of surfacing facts that are sort of very difficult to learn very easily. So now if we use this approach, which we call entograph, you see very nice scaling performance improvements. And importantly, we significantly exceed the performance of GPT-4, which was our teacher model here. So this is not really just distillation effects where we're just kind of learning things that the teacher knows. This augmentation is really, doing much, much better in terms of knowledge. Okay. One thing that was exciting to us was that, you can use this thing to essentially have models that generalize just like a LLM. Like the model now has this knowledge and it can use it in context outside of QA. It can do summarization. It can it can use that knowledge in other sort of questions that are not related to the book. It can do also even surprisingly weird things like compare and contrast two books that appeared in the data set, even though we never explicitly trained the model to be able to compare and contrast some of these books. So in the last few minutes, I want to talk a little bit about, trying to put this on maybe firmer foundations. I think, as I said earlier, synthetic data has this sort of mystical quantity. Whenever there's a hard problem, people are like, oh, yes, synthetic data will fix it. Don't worry. And that has bothered me a little bit. So I wanted to, along with my students, think a little bit about what is actually happening here, right? My point of view, at least for this style of synthetic data, is that it's really data augmentation, right? We're taking a document, we have a rephraser, and we're just sort of extracting the invariances out from the rephraser, and we're getting augmentations of the original data. So what does that mean? So imagine we have a graph, a knowledge graph, that contains direct mentions of entities. And then Entigraph, the algorithm we propose, is really just taking implicit facts and making them explicit. So how much extra knowledge might you be able to extract through this process? Well, this is equivalent to essentially just filling in a graph on some sort of random graph. You start out with a random graph, you pick two random entities, and you try to connect the two. Whenever there's a path, you end up being able to say something about those entities, so you make a direct connection. We assume that sort of there's no generalization in these facts, so learning is all just memorization. We're able to show something, basic but somewhat interesting, which is to say, there are both optimistic, upper bounds and nice limits to this process, right? If you start with something like a Erdős-Renyi process where you connect, facts between random entities, you can sort of fill in all of the connected components. And so that gives you limits on what you can do with synthetic data, but also those limits are actually pretty loose, right? If you have a really nice connected graph, you can learn all of the different implicit facts that are contained within it. I'll go over this very, very briefly, but you can use this to essentially get a kind of a new scaling law, which is a mixture of exponentials. It fits the actual observed data well, although this hasn't really been carefully sort of tested in an extrapolation setting. This is really just curve fitting. I'm just showing you that the curve fits well. Okay, so putting this together, I think a really interesting question that this raises, I think it raises sort of two different observations that maybe you can take home. First one is just the staggering difference between sort of human-like learning and LLM learning, right? With humans, you put a book in front of them and you ask them to read it and learn it carefully, they can kind of learn from a single book, right? If they really, really want to. Whereas with a language model, they can't really learn from a single book by just predicting the next word, no matter how many times you loop through that book, right? It's just a staggeringly different thing. The other thing I want to emphasize is that this is not kind of a fundamental limitation, right? Like synthetic data, even just basic things like rephrasing can really extract a lot more data efficiency and allow us to adapt to these new kinds of niche potential domains, which I think is a really interesting thing. And so this is a exciting testbed for data efficient language modeling, but also I think it's hopefully showing that there's a lot more upper bound to pre-training than maybe we have seen. So I want to end very briefly with some sort of more speculative but hopefully fun things that we've done since then, which is, I think both of the works that I've described have this flavor of using a really strong model to be able to, make little models better. And of course, in the second part of the talk, the little model ends up being stronger than its teacher, so that's good. But really, we would like to ideally understand bootstrapping process where we're not relying on a stronger model at all, right? That would be the relevant context for a lot of these companies like OpenAI. And so one of the things that we started to do with some colleagues at the University of Toronto, so Chris Madison and his student Youngjin, was to essentially see if we could bootstrap this thinking process. So we have some observed data, which is a very short compressed summary of a latent thought process. The thinking is, if we could sort of identify this latent thought process using classic ideas from latent variable modeling, could we get more data efficient learning algorithms? So this is essentially using some of our observations about synthetic data and then asking, can this lead to fundamentally more data efficient algorithms? I know I'm short on time, so I'm going to skip some of these processes. And I think one of the things is that it does kind of work, this process of essentially having a model try to identify some latent thoughts and then training on those latent thoughts and repeating that process can give us improvements in model accuracy in data-bounded settings. Okay, so just to put everything together and sort of to connect this to the bigger picture, right? I think I think it's been kind of remarkable being in language modeling and thinking about these scaling questions, because a lot of the really hard questions of generalization, really, these models made progress in a very different way. By having more data, by doing pre-training, and then adaptation, they were able to solve a lot of these multitask problems that I thought were out of reach for many, many years. And so today I wanted to really study some of those phenomena. And so the first part of this talk, what we showed was that, synthetic data is a really useful tool to try to understand some of these very mysterious objects like reasoning models. In the second part of the talk, I wanted to really try to push things and say, can we build much more data efficient models? And we showed that it's possible to do so by essentially coming up with new data augmentation style synthetic data methods. Thank you.
Hi. Thanks for the great talk. So I'm wondering to what extent you think that catastrophic forgetting is a big issue in reasoning training, because we're really focusing reasoning training on math and code data. My assumption is that knowledge in other sort of domains is being distorted. So yeah, should we be benchmarking this? Does this matter? Should we intervene in training, or should we just use different models?
Yeah, I think catastrophic forgetting is I would say both a problem and not a problem in the following sense. I think a lot of the modern LMs are really, really large. They're over-parameterized in many ways. And so it's possible, I think, for example, new reasoning training and the pre-training to live together. But I also think that kind of recent trends in how people train these models are going to make that a more important problem in the future, because the models are getting smaller because of inference cost concerns. And also post-training, which is how you inject these reasoning capabilities, is becoming larger scale. And so more and more compute and more model updates is being spent there. So I think up until now, it hasn't really been as much of a concern. A lot of these updates have been lightweight. These models are really big. But as people really try to push the size of the models down and do a lot more RL, we will have to think a lot more about it. I think thus far, a lot of those problems are solvable with more compute by replaying pre-training as you do a lot of the post-training stuff. It'll be interesting to know whether there's limits to that, or if there's more computationally efficient ways we can do that.
Thank you.
Thank you. Hello. So I thought to conclusively know about whether test time scaling works, we should look at more than 8,000 tokens. I wonder if your group has done that.
Right. So, I mean, we have certainly scaled that plot to the right, but we already have diminishing returns at 8,000 tokens. And so, I can draw you the flatter plot. But we sort of terminated that plot at 8192 because there's no gains past that point.
All right. Yeah, because so that was what Limo and they found too.
Right.
Is the baseline where at the bottom graph, you only run it through the books one round?
You mean the rephrasing?
So the flat curves. Did you just...
Oh, no, we optimized over epochs and replay and all the hyperparameters that are sort of relevant.
So if I have 1 million tokens in the books, did you just run it through 1 million? Or did you run the books many times?
We optimized over the number of passes over that. So I think over the grid of 1 to 10, we checked every epoch count and then we picked the best one.
So no matter how many times I run through the books, it's all completely flat?
Yes.
Okay, cool, thanks.
Or it's not flat, actually it gets worse.
Okay, great talk. I have a lot of questions. So one, did you reference textbook is all you need? Did you guys research that?
Or yeah. So we're aware of Phi. Although, I mean, maybe I can channel my frustration and say they don't really release very much like OpenAI either. We talked to Seb pretty early on for a different context, and we were like, can you give us your synthetic data? And he was like, no, sorry, it's all proprietary. So, we've been in touch with them, we read their papers, but it's sort of a different jam as well. Yeah.
Got it. And the second question, how this compares to RAGs?
Yeah, okay, that's a good question. I didn't put that slide in the interest of time, but I think there's sort of two things I'll say about RAG. The first one is scientifically, the question that we're interested in here is, putting knowledge in parameters. And so we think that's interesting as its own goal. That's one thing I'll say. But the second one that's cool is this intervention composes with RAG. So we get, I think, 2 to 3% accuracy boost on top of a really, really strong, almost Oracle RAG retriever in this setting. And so you would want to do this if you're resource rich, even if you're doing RAG. And then the gains that we get through synthetic data, continued pre-training, is roughly 80% or so of the gains that you get with RAG. So we're getting most of the gains that you can get out of a strong retriever.
Yeah. Yeah, thank you, Tatsu. Great talk. I have sort of a broader question and a more specific one. So it seems like a lot of the recent work is focused on like trade-offs between data and compute efficiency. And I think it's really interesting to see an approach here where like we can use less data, but use more compute and get those gains. I guess my broader question is, what are your thoughts on trying to improve data efficiency without needing to incur such a large computational cost? I think you touched on this a little bit towards the end of the talk, but would love to hear more. And I guess my more specific question is, when you see these diminishing returns around like 8,000 tokens, do you think this has anything to do with the context size? Like if you triple the context size, can you then improve the length of your chains of thought that you can use to get better improvements?
Yeah, so I think the first one was about sort of computationally efficient, data efficient models, I guess. Yeah. I think that's interesting, and in some ways I think that's the right approach, in the sense that we know that humans, when we learn, aren't doing this like kind of crazy, like let's generate, 1 billion extra synthetic tokens and then learn on that data inefficiently, right? I think this is kind of the safe way to get it to work today. But I think long term, the right thing to do is to think about architecture or algorithm interventions that get us more data efficient learning. That would be lovely. I just don't think right now we have even the right paradigm for that yet. For the second thing, I do think it would be really useful and interesting to be able to get this kind of sort of longer extrapolation. Wait 1 second. Let me think about. I think the issue is that we haven't really seen very much extrapolation, even in like loop transformers and other kinds of like new interesting ways of extrapolating reasoning thinking. We've seen very similar issues of like kind of stopping roughly where your training compute is. And so once we have paradigms that go beyond that, then maybe it's possible to sort of think a little bit differently.
So I have a much more informative kind of question. So I understood what you meant by synthetic data in your second part, which was this augmentation. But what was the synthetic data part in the first part of the talk?
Yeah. So in that part, what we're doing is we're essentially using Gemini flash thinking to construct the reasoning traces that we then train on to train the model. So it's just distillation, right? I mean, synthetic data, I think, gets used in several different contexts. We actually have all three kinds in this talk. One of them is distillation, which is part one. Another one is kind of data augmentation, which is part two. And actually, the last kind is self-training, which is the bit that I skipped at the very end there.
Okay.
Thank you for a great talk. I found the way you use the knowledge graph to augment your data very interesting. But compared to human reading of a document, when we read a document, we augment not only by generating additional relationship between the entity, we augment by combining with our common sense knowledge base, our awareness of the surrounding world, the world knowledge graph, right? Wikipedia, our life experience. So have you thought about combining knowledge graph in addition just a single entity graph extracted from that domain document?
Yeah, I think that approach of thinking about sort of having the model put in everything that it knows is the right like broader approach to this. I think the knowledge graph approach was what we did primarily because it was kind of cleaner. And also we were very, very worried about distillation effects in that second part. We're using a very strong model to generate data for a weaker model. And so if you let the strong model just like use all of its knowledge about the world, then now you've got sort of information leakage. And so we wanted the model to be as kind of an agnostic rephraser as possible and only use the data in the document as a proof of concept. But I think if we were to go and like kind of deploy this out in the world, we would do exactly what you're suggesting of saying.
Interesting to say empirically.
That's right.
Okay, last question.
So in the last approach to the synthetic data, which is bootstrapping with the same model, how do you not hit the data processing inequality limits?
Yeah, I mean, okay, so I'll just answer the data processing inequality limit part in general rather than the specific of the project. I didn't talk about it. I actually think data processing inequality arguments are very, very weak ones for synthetic data. Mainly because if you think about the information theoretic limits of pre-training on the internet, for example, that's actually really high, right? It's like every fact on the internet plus every fact entailed by facts on the internet is the information theoretic limit. And so if we're making information theoretic limit arguments, I think the bounds are very, very loose. That's at least my opinion for sort of synthetic data bounds. Whether we can attain them is a totally different story. But I do think those aren't really providing strong limitations, at least for knowledge aspects of synthetic data.
And a follow-up question, do you think the similar argument applies to vision models and sort of like a multimodal sort of reasoning?
Yeah, I think vision models are interesting because in many ways they started out much more ahead in terms of data augmentation. Like if anything, language people are learning from vision people about all these data augmentation things. But I think, the generative models we have today, now the situations are a bit reverse. Like text models are much more controllable, precise generators than image models. I do think with the newest generation of like autoregressive image models that are like much more controllable, it might be the case that actually we'll see a lot of like image synthetic data work as well in the same vein.